At this stage, you should understand dimensional and geometric tolerances and be able to interpret what the design specification is saying about that. Now, those aren't the only specifications, so what we'll look at today are some additional ones that you should pay particular attention to because they're going to affect your manufacturing system. Let me wrap up the geometric tolerances with a couple comments. One is when you see a feature control frame, in other words, a geometric tolerance, it's like a highlight. It's telling you you have a critical feature in the design spec. So you need to pay close attention to that. And secondly, you need to make sure that everything is clear about the use of dimensional tolerance versus geometric tolerance. By that I mean if you are controlling position with a position geometric tolerance, you should not be controlling position with a dimensional tolerance. Again, they could be in conflict. Same thing with angularity. If you are controlling orientation with some type of orientation tolerance, you should not be controlling that with a dimensional tolerance on the angle. Okay, enough said. Let's take a look at a very important specification, and that is, you'll find it on pages 102 to 111 in your text, surface texture. Now, the reason why surface texture is of great concern is because it always implies that there is secondary processing, some type of finishing operation, to create a specific surface texture on the part. And what we're doing here is controlling a much finer level of details, what we call these irregularities of the surface. So we're not looking at geometry now, we're looking at very small deviations in the surface. The two types are roughness and waviness. And if you look at a surface, the roughness is the smaller high-frequency irregularities. So it kind of looks like white noise. And then the waviness is more the low-frequency and higher deviation irregularities. When we look at a surface after one or more processes, we might see some type of pattern due to the effect of tools on the surface. And that pattern is what we call the lay of the surface. Now, you should have seen some of this in 248, so hopefully this is primarily a review at this stage. Then we can just have outright flaws or marks, dings, and scratches on the surface that are unusual and appear randomly and do not have a pattern. Here's an example of a surface. Note the scale. The scale here is microns. So we've got X and Y, and we've gathered data across the surface. You can definitely see the lay here as the tool, which is a fly cutter in this example, and you can see the magnitude of irregularities on that surface. So we have peaks, which would be the high irregularities, and then we have some valleys, which would be, as you can see in this region here, we've got some significant valleys, and then we've got kind of in between here, but the lay is very pronounced. So if you had a surface texture specification on this, you might want to eliminate this pattern and make it a smoother surface. Here's an example of an end mill which you used in 248 on a number of your processes, and the lay is very pronounced here, which is not surprising based upon what you know about the geometry of the cutting tool. Again, what we have here are regions where we have high peaks followed by valleys in between. And so we see a definite lay pattern with the end mill. Now here's a surface after a grinding operation, and as you know, grinding is an abrasive operation, but there are traces of a lay, as you can see, that have not been fully removed. But as you can see on the surface, a significant portion of that surface is consistent in terms of its deviation and irregularity, which is not surprising because grinding, again, is a finishing operation. So here, we see our lay pattern is still somewhat there, and so we might want to go back through and grind this part again. Well, you have to know something about the roughness determination in order to determine whether or not your part is within specification. So we think about the nominal profile just like we did in geometric tolerances, and that would be the basic profile of the design surface. What does that look like? And then we use a graphical mean line to kind of fit the actual profile, and it's going to be parallel to that nominal profile. And we'll fit it such that we have equal area on both sides of the line. So here you can see we've got a nominal profile for a surface. We orient the graphical mean line parallel to it, and then we're going to measure the actual deviations or irregularities on the surface. Notice we're not concerned about geometry, we're concerned about these deviations. So when we mean that the area is the same on both sides, essentially the integral of that, the area on the top should be the same as the area on the bottom. And that defines where this line is located. So the line moves up and down depending on how much area is on the actual surface. Now, you know, when you did this in 248, you measured surface roughness, you took a scribe essentially, which rode along the surface, and you dragged it across the surface, and you produced this blue irregular curve here, which represented one set of data in a line going across the surface, and then you could repeat that multiple times. Well, how do we come up with a metric that would tell us something about that roughness? One of the most common ones, and you should have seen this before, is roughness average. And that is going to take the absolute deviations, as you can see here, from that graphical mean line. And we add them all up and then divide through by the length. The length would be the length over which we've collected data. Well, the value for n will depend upon our ability to collect data. So how fast can we collect data as we drag the scribe across the surface? And so this could be quite a large number of epsilon sub i's. Notice it's the absolute value, so it's positive in either direction. So it really is a measure of area, the top. And then we divide through by L, so we've got a time average, or I should say a length average, because L is in the denominator, an average deviation from that graphical mean line. Notice we're not trying to locate it at the nominal, just parallel to the nominal. Another one that is popular is RQ, which looks at the variance. So it's one thing to talk about an average. As you know, the variance can be significant, and so it's nice to have both pieces of information when you're looking at these irregularities. In order to get a measure of variance, what we'll do is square those deviations instead of taking the absolute value. And again, we use the same set of epsilon sub i's, square them, and divide through by L. So we get an average over that length of the epsilon sub i's squared, and this is kind of a measure. It's not obviously exactly the variance, but it's a measure of sigma squared. Note that all these terms will be positive, and n is the same as in the previous example. So two different measures tell you two different pieces of information. If RQ is small, then you don't have to worry too much about the variation. You can use R sub A. If RQ is large relative to R sub A, then you would have some concern. Now, how do you know that you have a surface texture call out in the design specification? What you're going to see is a symbol, and the default for that symbol will be roughness average, and that's why you'll see it as the most common type of control. The maximum value for roughness is specified. So again, R sub A has to be less than or equal to this value. Also note that we take a very small sample of the surface. The typical length for L is 1 millimeter or less. Extremely small. Now, of course, you might take multiple samples, but you can see we're looking at a very small sample on the surface. So here's some of the symbols that you'll see. Again, the very basic form of that is just this check with the value in there telling you this is the maximum RA that you can have. And then you might see a closed triangle here indicating that you have to machine the surface in order to achieve that level. We can also specify how much material should be removed. And again, this is all in terms of microns. So we're talking about a very small unit here. And if you don't know what a micron is, that's something that you might want to look up. If you put a circle in there, then what you're saying is you can't remove material. And so you're going to have to use a different process than a machining process or a grinding process. The general symbol, which would include a specification of the pattern for the lay, would look like a square root symbol, again, R being the maximum value, A being the removal allowance that can occur on that surface, and then L would be strictly enforcing a lay pattern for that surface. Here are the different types of lay symbol if you're trying to specify a specific lay. Here we think of the relationship to the profile. Again, you have to think about the surface. What does the profile look like? When we say it's parallel to the surface, then we're indicating that. If we're saying that's perpendicular, X would be angular in two directions. M would just be multi-directional. C would be circular, so you might see a pattern like that. And then P would be none, so really there's no point in having a pattern there. You want to remove any vestiges of a pattern such as this, so we might grind and then polish that surface. Okay, so here's an example of what you might see on the design spec. How do we know that we have surface texture? And of course, we're concerned about that primarily because this will be a costly operation. It's going to add significant cost to our part. And it will also increase our lead time to produce this part, as we'll see later on. So we're looking for our checks indicating that there's a surface texture specification. And similar to what we saw for geometric tolerances, we're looking at a leader in this case that's attached to a specific surface, and we're saying that those surfaces, which would be this surface and this surface, which turns out to be a 2D annulus here, is going to have a maximum RA of 125 microns. And then we look out here, attached to this extension line, which means, again, I've got a 2D annulus about that cylindrical feature, the through hole. And then on this side, the same thing. I have a 2D annulus that has a specification. Both of them are 125 microns for R sub A. So that means when we get to the manufacturing processes, we'll be doing, most likely be doing finishing operations on those surfaces. Here, we don't see any specifications in terms of surface texture. Here we note, again, this is the same part we're just looking at from different perspectives. Here we note that we have a check there, and that's the only one that appears on this view. So we've got 125 microns. What is that attached to? Well, you can see here we have a boss, which is on a through hole. And so we're going to have a 2D annulus whose RA has to be less than or equal to 125 microns. Again, you're looking for the extension line, and then what surface is it attached to? Besides surface texture, another important feature that we should be concerned about, and we've already talked about this before, and that is a thread. A thread is problematic in terms of extra processing and ensuring that you're getting the proper threads for that feature. So it adds cost and time to our total lead time. There are a number of ways to specify threads. A common form, you'll see the UN designation. And if you look in your appendix in your book, you'll see a table giving you the unified thread characteristics. You'll get a nominal size with a thread per inch, and you'll see a UNC designation, which indicates a category of coarse threads, or UNF, indicating you have fine threads, in other words, more threads per inch. H is going to be the height of the fundamental triangle, the profile of the thread. Then we have flank angles, also related to the profile of the thread. Then you have major diameter, pitch diameter, and minor diameter. Now, as I said before, the tolerances for threads are attached to the thread specification, and those tolerances relate to these three characteristics. The major diameter indicating the larger size, the pitch diameter in the middle, and then the minor diameter towards the smaller end, and we'll see what that looks like in the geometry. Most important characteristic beyond those is the threads per inch, which is related to pitch through this relationship. Again, pitch is the distance between threads. So if we look at the geometry based on those parameters, we're going to see something like this, where again your thread tolerances relate to major diameter, pitch diameter, minor diameter, which correspond, we're looking at a side view of the thread with these locations on the thread. So we get some type of tolerance on these, some type of allowance for the location of those diameters. And that's why it's problematic if you see a thread feature that is being controlled with a geometric tolerance and you use an material condition such as M. Question is, and a lot of confusion, which value, because you can only use one number for your tolerance zone, which tolerance value do I use? Do I use MMC for the minor diameter, MMC for the pitch diameter, MMC for the major diameter? Whichever one you use, and some people might argue for the pitch diameter because that's kind of like using, in a sense, the midplane, but that doesn't guarantee, of course, that your minor diameter and major diameter are controlled. So if you plan on using that M, then of course it should be clear what you're referring to in terms of the thread tolerance. Here's a table out of your text. You can see we've got threads specified in terms of the major diameter here, and then we have the threads per inch, and in the UNC specification up to 0.216 for the major diameter. Our specification is based on just a number. So you would just see a 0 there. So in this context, we've got an 8. And that 8 corresponds to this thread. And then the 32 tells you you're dealing with a coarse thread versus a 36. Note that there are a finite number of combinations here based upon the major diameter and threads per inch. Then when we get to larger major diameters, we'll actually put the value in there. And as you can see, these are English units. Well, those aren't the only way to specify threads. Another common form is the metric thread. And here's your hint. If you see an M there, then it's indicating that you have a metric thread, followed by the nominal diameter, and then the pitch, and then the tolerance class. Again, similar to what we talked about, tolerance for the UNC. D nominal, P pitch, that's the distance between threads, and then T being the tolerance class. So here we see an M2. By definition, an M2 has only one possible pitch, and that's 0.4, versus an M16, 16 millimeters in terms of nominal, and then 1.5 for the pitch. And then we have our tolerance class of 6G. Again, if you see a UNC or metric designation for thread, you definitely be aware of that and the implications that it's going to have in your processing. The final symbol that I'll bring your attention to is welding symbols. The weld symbol will tell you the weld type. The welding symbol, which is no slight difference in the term, but it's going to give you all the details on the weld. So I have to know the type of weld that needs to be performed and the details of that weld. Well, you could take a whole course just in welding symbols, and that's not the focus of this class, but I'd just like to point out some common types of welds that you might have seen in other courses: a spot weld, a fillet, a square groove, and a bevel groove. These are indicating the actual processing that's going to take place, and it's in the design specifications. So your work has already been done for you. You already know that you're going to go through a welding process, and so you should begin to think about your concerns related to welding and what needs to be controlled there in order to achieve the characteristics of the product. The welding symbol as opposed to the weld symbol, right? So we just looked at some weld symbols, and that weld symbol goes here and here. The type of the weld for this side of the joint, right, can be specified on this side, and if you look at the line on the welding symbol, that's supposed to represent the joint that you're creating. So I would put it on both sides if I wanted to indicate the type of weld on each side. And then, similar to what we saw for the profile tolerance, if you have a circle there, it means to weld all around whatever the joint is. And then we could have a process specification of some kind. Note again, there are many variations on the specification for basic welding symbol. My recommendation, unless you're going to invest the time in becoming an expert on these welding symbols, and that would depend upon the extent to which you're using welding as a process. So if all your parts involve welding, that would be a wise investment. But if it's infrequent, then my recommendation is to consult with a welder who has had training on those welding symbols and is aware of some of those implications. So, in summary, when you look at a design specification, at this stage it's critical, and I mean critical, that you understand the details. Do not assume. By that I mean do not read into the specification things that are not there, things that are not specified. If things are not clear, ask, find out. Don't start on the next stage of engineering and not realize what you're trying to accomplish here. It's also your responsibility to check that specification. And you need to check it for completeness, such as your feature control frame has everything in it that you need to understand what's being controlled. And that there's no question about what's being controlled. There's no ambiguity. And that goes for any symbols, welding symbols, surface texture symbols, whatever they might be. And that those specifications are valid. In other words, there are no conflicts with other specifications, and they are correct. They have the right definitions, and there's no problems associated with them. And then finally, if you understand the details, then you start to evaluate what's the impact on manufacturing in terms of processing. What's it going to take, which is what we're going to look at next.